Hi everyone, this is the mechanical power video for thermodynamics. So, what is mechanical power? It is simply the rate of doing work. Doing work, mechanical power. So, it's indicated by W dot. We've talked about that in a couple of videos now. So, thinking about the rate of doing work. So, our work is something like kilojoules or joules or BTUs or something like that. And then we put it per unit time. So our units in that case look like horsepower, BTU per second. It could be a foot-pound force per second or minute. It could be a watt. It could be a kilowatt. Could be a joule per second, which is a watt. So that's what our units are going to look like for mechanical power. So again, thinking about work per unit time. It's a rate of doing work. So let's think about what that means in terms, or I guess what that looks like in a common application in thermodynamics, which is in a turbine or a turbine. They are the same thing, just different pronunciation. So if I say it different, turbine, turbine, I mean the same thing. So let's look at a turbine. And in a turbine, this fluid is coming in as a usually superheated vapor or just a saturated steam. So it's a high pressure, high temperature steam. So then it's going to go, what happens in a turbine is it's going to go through a nozzle, which going back to fluid mechanics, if you put something through a nozzle, you're going from a bigger diameter to a smaller diameter, it's going to make it go faster. So this high pressure, high temperature steam's going through a nozzle, it's going to be going really fast. And there is some sort of, I'm going to draw it as blades here. That kind of looks like a flower, but it is hitting blades that is then making this shaft spin. And in that turbine, there's not going to be just one set of blades. There's going to be multiple sets of blades. And so those are called stages of the turbine. So this fluid's going to hit that, and it's going to cause that turbine to spin. It's going to cause those stages to spin, which is turning this shaft. And how you can think about this is like, you know those merry-go-rounds that are in parks that you could grab on and you could spin it? That's kind of what this is doing, is it's hitting those fan blades, those turbine blades, and it is spinning these to make this shaft turn. And what comes out here is called the exhaust, which it's going to be a lower pressure. If we think about our TS diagram or PV diagram, we're kind of going from that high pressure, jumping down to that lower pressure. We'll get much more into that. You'll be able to visualize it. But we're going down to a lower pressure fluid coming out of there. So basically, you are taking the energy, high energy coming into the turbine, and you are transitioning it into being able to spin a shaft to create power, ultimately. So the equation that you got in dynamics, so for shaft work, is torque. Oh, I didn't do my T right. Hold on, torque. Bad erasing here. You got to do the little curve. We got to do our tau there of torque times the angular speed. So torque times angular speed. So that is where your foot-pounds comes in times something like radians per second. And we know radians aren't really a unit, so we get foot-pounds force per second, which if you go back up here, that's one of the units we're looking for mechanical power. So the rate of doing work works the same as your dynamics definition here of how we're going to get what that power is. let's look at it in terms of how we are going to calculate it in our class, because we are not going to use this equation directly to be able to calculate that. So how do we calculate it? Well, let's go to our overall energy equation here. So again, this is our simplified form that we got to from the first law of thermo. Follow all the videos up to this point, we get to this simplified form where we have, this is the stored energy coming in, and we've gotten rid of potential energy, we've gotten rid of kinetic energy, we've combined the internal energy with the flow work to come down to our mass flow rate times our enthalpy. So we have stored on both of these ends. And then thinking about in a turbine, we are not doing work on the fluid. We are not transferring Q into the fluid. We are getting work done by the fluid, so we're going to leave that one. And in this class, we're not going to pay attention to this. There is going to be some Q loss just because of the nature of you're at a really high pressure and high temperature. You're coming out at a lower pressure. There are implications for the Q, but for this class, we are going to ignore Q out for the sake of right now. And so our equation comes down to, let's go back actually to work by, if we move this over to the other side, move mass and H out to the other side. Oh, well, this is the work of a turbine. Let's do that. Is equal to M dot H in minus M dot H out. So that's going to look like, let's just put the mass flow rate together because it's going to be the same mass flow rate. Again, going back to fluids, conservation of mass, our mass flow rate in is going to have to equal our mass flow rate out if we're running this at steady state. And so you're going to have the H of the superheated vapor, or the high pressure, high temperature steam up here, minus the H of the exhaust, which is again a lower pressure, lower energy fluid coming out. And so that's going to be our equation for finding the work by a turbine. And you can do a similar thing for a pump. So let's do a just brief overview here of not walking through every step, but you'll draw a pump like this. We are putting work on a pump. We are paying that bill to plug that pump in and make it run. And we are coming into this pump, we have a low pressure liquid, and we are going to come out with a high pressure liquid. And so because of that, think about this simplification. We're still going to have our mass flow rate in, mass flow rate out, and the enthalpies associated with that, because this is going to have some energy coming in. It's going to have some energy coming out in this actual fluid. We are now doing work on, and the rest of these assumptions are the same, because again, pumps, the goal of a pump is to not change the temperature of the fluid. That's not why we have a pump. Is there going to be a little bit of a residual change in temperature? Yes, but we're not worried about that. We're worried thinking about the pressure and the work that we have to do here. We're not going to have work by, because that's what a turbine does. Still get rid of, both Q's. So then our equation looks like work on, which is the work of a pump, is equal to, again, think about our signs here, is work on. So now I'm going to move my mass flow rate H in and mass to the other side. So let's go mass flow rate here is going to be H out is our positive one this time, and H in is on, or is the negative one this time. So H of the, let's call this the exhaust. So coming out of the pump, you don't usually call that an exhaust coming out of the pump, but just trying to think mirroring this of, this is the higher energy is coming out. Pumps increase energy, turbines release energy because it's getting converted to something else. So there is your mechanical power video.